Okay, so we have the next talk coming from Saurabh, and as you can see, we're going to hear all about supernovae that involve white dwarfs from the observational perspective.
Okay, thank you very much, Sylvia. Thank you to all the organizers for this somewhat daunting challenge in 20 minutes to summarize this subject. Literally every slide I have could be or has been its own conference. So I'm going to apologize in advance to people I see in the audience if I don't discuss your favorite paper. Most of what I will talk about is in fact a review of other people's work. So let's get started. If you want more, Kate McGuire, Mark Sullivan, and I wrote a little review article about recent advances in observational properties of white dwarf supernovae, thermonuclear supernovae in Nature Astronomy a couple of years ago. So you can have a look at that article. Okay, so indeed, the subject, what is the subject? I did not say type 1a supernovae. I said white dwarf or thermonuclear supernovae. And let's say, first of all, that there's a very limited direct evidence for exploding white dwarfs. So maybe a couple pieces of evidence is in supernova 2011 FE and M101. Just based on the early time rise of the light curve of the supernova, you can get a limit on the size of the progenitor star. And that seems to be much smaller than a tenth of a solar radius. So again, implicating a white dwarf or potentially smaller. And then direct evidence in gamma rays for gamma ray, in this case, cobalt lines, which are thought to come from the fusion products. Okay? But other than that, exactly the evidence that we did not directly see a white dwarf explode, and so we only infer that these supernovae are in fact white dwarf supernovae, meaning what is the thing that explodes, or thermonuclear supernovae, meaning what is the power source. What is the energy source that we see. Okay, but there is significant indirect evidence, and I'm sure this is familiar to most of you. So for instance, I've shown you some spectra, either at early times or at late times here. I hope you can see my pointer. They're quite homogeneous, and they are consistent with the predictions for fusion of degenerate carbon and oxygen. The light curves of type 1As, the bolometric light curves follow the radioactive nickel-56 decay, first suggested by Titus Pankey in his PhD thesis. I encourage you to look at the history of that. It's quite interesting. Unlike core collapse supernovae, we don't ever see a massive star progenitor for type 1A supernovae. In supernova remnants, where we think it's type 1A, and in some cases where we know it's a type 1A from light echo observations, we don't see a compact object like a neutron star or pulsar in those remnants. Okay? And of course, these type 1A supernovae can occur in old or non-star forming solar populations, unlike the core collapse supernovae typically. Okay, so all of this is pretty strong, I would say, indirect evidence that we really are talking about exploding white dwarfs. Okay, so of course they are important also for distances in cosmology. So type 1A supernovae are standardizable candles. The luminosity is correlated with the light curve decline rate and also with the color. And so on the left here, you can see that behavior with the decline rate in various optical bands, what's called the Phillips relationship. Modern uses of this technique to measure distances for cosmological applications use what's called the trip standardization with the SALT-2 model. And that basically has three parameters: a peak magnitude, a light curve shape parameter here called X1, and a color parameter C. And then there's some coefficients that regress out the light curve shape and color. I wanted to point out one thing which is not that well appreciated, I would say. Oh, by the way, on the left-hand side here, you can see what the model looks like, fitting some actual data. This is from the SN Cosmo package. But one thing which I think is not fully appreciated is that normally people think that the luminosity variation with light curve shape, meaning the subluminous and the overluminous supernovae, that dominates this correction. But that's not really true nowadays. For cosmological samples nowadays, we mostly focus on a relatively narrow range in the parameters of light curve shape and color, such that if you actually look at the coefficients and multiply by the range that people pick for the cosmology, it's in fact the color that gives the largest correction. So the correction from color is beta times C, something on the order of a few tenths of a magnitude up to 1 magnitude, whereas the light curve shape correction is actually smaller typically than the color correction. So just something to note. Okay, so what do people do with these distances that they get from 1As? Of course, you've heard this story, I'm sure. So we can apply it to high redshift supernovae, which is a differential measurement of supernovae nearby in the Hubble flow, and then at higher redshifts when the expansion history of the universe has changed in the past. And of course, this was the first great evidence for dark energy, the accelerating universe. And that whole program has continued apace. Here you can see results from the Pantheon sample from Dan Skolnick et al., combining a bunch of different surveys, low redshift and high redshift. And you can see that the constraints here are really tightening in on a flat universe with an equation of state for the dark energy that's fully consistent with the cosmological constant. And of course, we'd like to push this down further in combination with other cosmological measurements to learn about dark energy. More recently is this idea of measuring the Hubble constant with type 1a supernovae. And just as a reminder, to do that project, you really need absolute distances to the 1As. And so you need to calibrate the distances to the 1As in some way. And unfortunately, there aren't enough 1As near enough where we have other direct geometric techniques to calibrate them. So we have this 3-rung anchor nowadays, where we have some geometric anchors, which then calibrate Cepheids, which then calibrate the type 1a supernovae. And the supernova part of this is really a differential measurement between Hubble flow supernovae and these Cepheid calibrated supernovae. And when you do that, for instance, in the SHOES project led by Adam Rees, you find this about 9% tension in the directly measured H naught that you get from this route with what you would predict for the Hubble constant today from observations of the early universe. For instance, the Planck measurements of the CMB and assuming lambda CDM. So that's really exciting because if it's true and there's no error in those both measurements, that implies that the weak link is probably this assumption of lambda CDM, that we don't understand dark energy and dark matter well enough, or how things are behaving in the early universe well enough, and that this could be a clue to this new physics. So that's why people are very excited. Now, I'm going to spend the rest of my talk talking about what we don't understand about type 1a supernovae. So it's a common refrain that you will hear is that, well, these supernovae, we're using them as standard candles, but how much can we actually trust them? And I want to push back on that, at least for this application, a little bit. And the reason is that the supernovae, I think, are not the weakest link here. If you're going to say this is not new physics, but this is just a problem with something in the local universe H naught, I don't think the supernovae are the weakest link here. And the reason is because the supernovae, again, here, it's a differential measurement between the calibrated supernovae and the Hubble flow supernovae. And so you need to have a systematic difference in these populations to create a problem in your distance ladder. And these populations are really just not that different. So for instance, the look back time to the calibrated supernovae, something like, these are 80 a million light years away, whereas the Hubble flow ones are maybe 8 or 10 times that. But still only a few 100 million light years away, a few 100 megaparsecs. And there's not that much time in the universe for the population of supernovae in the Hubble flow at 200 megaparsecs to be that different from the population at 25 megaparsecs. I'm not saying it's impossible, but it's pretty hard. And we also work hard to try and make these samples as similar as possible. It is a challenge to get this big of an offset just from the supernovae. For instance, here you can see that I've highlighted places where the supernovae are being used with different calibrators. And you can see, for instance, there is a little bit of offset here between the green ones, which use Cepheids, and then the purple ones here, which use tip of the red giant branch. For instance, the Carnegie Chicago project led by Wendy Friedman's results. And so there, the difference is not the supernovae, it's the difference in what you use to calibrate them. So a difference between Cepheid distances and TRGB distances. Okay. So I would say the supernovae are not directly implicated in this right now, but of course, we still want to check that. And there are many things that people are doing to check that. Okay, so one example, perhaps, what is the place where the supernovae could make a big, have some sort of effect? And I won't go through all of these plots, but there seems to be this relationship between the standardized luminosity. So after you've made that kind of SALT 2 trick correction, there seems to be a relationship between the standardized luminosity and the environment of the type 1a supernova. So for instance, that could be parameterized by the host stellar mass. So that's shown here. It could be parameterized by the star formation rate at the location of the supernova or the stellar ages. There's lots of papers on this. Okay? But they all seem to suggest that even after you make this standardization, there may be some differences that reflect the underlying population. Okay? So lots of papers here, and as I said, you can have a whole conference on this subject, and that has already happened. The upshot here, I would say, is that this is very interesting. I think it's actually hard for this to make a large impact on H0, or at least large enough to be the explanation for the H0 tension or crisis, or whatever you want to call the Hubble constant problem. But it could be a bigger issue for dark energy and constraints on W, just because you have such a long lever arm for evolution in the history of the universe. So that the samples of supernovae you're going to have at high redshift could be very different than the ones you have nearby. Okay, but this is already kind of in the weeds, this idea of standardized luminosity. Maybe, for this conference and this crowd, it's probably interesting to look at the fact that type 1a supernovae properties, even before you standardize them, even before you try and make them into good distance indicators, are connected to their environments in ways that we do not understand. And so here are some plots from a recent paper by Rutgers PhD student Kyle Detman, which is just the latest in a line of this kind of exploration. Of course, I wanted to show my own students' work, but this just has a lot of data points on it. But what you can see in the left plot here is the silicon velocity. So that's a measurement of the silicon velocity, the silicon line in the spectrum of the type 1a supernova. So it's really directly connected to the kinetic energy and the ejected mass of the explosion. So very, explosion, intrinsic property of the explosion, the speed at which the ejector are coming out, versus the stellar mass of the host galaxy the supernova was in. Okay? And you can see the strong effect that the high mass hosts seem to give you supernovae with all sorts of ejective velocities, whereas the low mass hosts only give you the lower, the normal, as we call it, silicon velocities. Okay? So that's strange. If you want a model of what is going on with type 1a supernovae, you should be able to explain this correlation, this fundamental link between how the supernova explodes and its environment. What is that link? Is it age? Is it metallicity? What is causing that? And how does that relate to that white dwarf and the binary system that it's in? Okay? And people have known about this kind of thing for decades already. There's also relationships on the right here. You can see between the light curve shape and the velocity, or the host stellar mass, or the color, et cetera, et cetera. Right? So there are these, and before standardization, there are these relationships between things we think are intrinsic to the explosion and the environment. We need to explain those. Okay, usually when people try and think about this question in terms of progenitors and explosions, the thing that comes up is people show exactly these two pictures of a single degenerate and a double degenerate scenario. And I want to try and impress upon you that is not the right, or that's not the only question that should be on your mind when you think about 1A progenitors. What we know probably is that a carbon-oxygen white dwarf explodes, but what we don't know is a lot more than what the companion is, whether it's single or double degenerate. We don't know the mass. Is it Chandrasekhar mass? Is it sub-Chandrasekhar? We don't know the companion. We don't know what the accreted material is. Is it hydrogen, helium? Is it other white dwarf material? How does the explosion proceed? Is it a subsonic deflagration that transitions to a supersonic detonation? Or is it a double detonation where you have a shell that detonates? Is there any interaction signature with the companion? And what is left behind, if anything? Right. So all of those are important questions, just as important as this single versus double degenerate. So we should think more broadly about what we don't know about 1As. Okay, so I just want to show some highlights of kind of recent observational discoveries or new pieces of evidence that apply to this question. So one is the fact that we have these satellites now like Kepler and TESS, which can provide a very incredible high cadence time sampling of early time light curves of these supernovae. So these are supernovae that are discovered from the ground, and then they go back and see, aha, Kepler or TESS happened to be observing supernova when it went off. Let's see what happens. And the idea is that if at early times the ejector from the supernova runs into the companion star, you should see that. And the bigger the companion star, for instance, a giant, the bigger the interaction signature is. Okay? And so indeed, in a few cases, we do see these early time bumps. And so that might be indicating interaction with the companion. But the answer, it seems to be that in most cases, we don't see that. Okay? And even in the cases we do, it could be just radioactive material that's somehow in the outer layers that's giving you a little extra luminosity at early times. So it's unclear what the cause of these early time bumps are. Okay? Similarly, at late times, people look at late times when, if, for instance, there's hydrogen around that was stripped from the companion, it should, mix a little bit with the radioactive nickel and get energized, and you should be able to see that when the ejecta thin out at late times. Okay, and again, you see this there are a few examples where you can see this kind of thing, but for most of the cases, okay, so here's a distribution of what what the estimate is for the amount of this stripped material. It's way down here, and these are the predictions for main sequence, subgiant, and red giant companions. Okay, so again, this late time interaction signature is also quite rare. And as far as we know so far, there are no radio or X-ray detections of 1As as described in these papers here. Okay? And so all of this is somewhat pointing to the idea that there's not much normal material that you would expect from a single degenerate scenario where the companion is a normal main sequence star or a red giant. And so maybe that's suggesting that double degenerates are the right way to go. But in fact, some of this, you might expect some of these kinds of interacting signatures even in the double degenerate scenario, where there's just material from the other white dwarf. Okay, so one other new thing I think, which is somewhat underappreciated, is that I would definitely like to call this talk about white dwarf supernovae or thermonuclear supernovae, and not just about type 1As, because there is this whole zoo of other white dwarf explosions. Okay, it's more than just normal 1As. And I won't go into the details of all these classes. You can read this great review article by Stefan Taubenberger about all of these different things. They seem to be quite similar, mostly in the optical, that indirect evidence that they are exploding white dwarfs seems to hold for these as well. They can be quite a bit different in the infrared, by the way. But so understanding, if we want to understand white dwarf supernovae, we need to not just understand the 1As and why they behave the way they do, but you would also want to explain all of these other peculiar cousins to normal type 1A supernovae. So one example, which I studied a lot, so of course I have to include it, are type 1AX supernovae, perhaps the most numerous of these peculiar ones. And there's a whole literature of this. I just wanted to show that there's lots of observational papers on this, and then many other theoretical papers, which I didn't even list here. And the model here is that maybe this is a CO white dwarf where the companion is a helium star, which in one case we think we've actually detected in pre-explosion observations, that this would be the helium star companion, the supernova 2012Z. And the idea is that maybe this white dwarf explodes as a pure deflagration that is somewhat low energy, that produces low velocity ejecta, and that does not necessarily completely unbind the white dwarf. Okay, so you can read more about this kind of object in a bit. Other recent observations, I would say one of the exciting things is this idea of whether the explosion of a white dwarf proceeds from the inside out, meaning you start with an explosion in the core, or is there a shell on top that detonates? And so in a couple cases, again, we see evidence in the spectra for a shell, either a thin shell, a few hundredths of a solar mass of helium, or a thicker shell, in this case, about 0.15 solar masses of helium, that detonates on the surface, and that might be the thing that drives the detonation of the carbon in the core. So one of our organizers has written a lot about this, and this great paper by Abby Poland also talks about this. The problem with this scenario, it doesn't seem to happen all the time. These kinds of signatures are quite rare, maybe only in 1% of the cases, as estimated by this paper by Matt Seaver. Okay, what about, what other observations of white dwarf-like things could, which, obviously are interested to people at this conference, could help us with this picture. So I think, one of the real highlights of work that I've been a part of, led by one of our organizers, Ken Shen, is this search in Gaia for surviving companions to type 1A supernova. So the idea that Ken had was if you have a double white dwarf system and you have Roche lobe overflow from the companion white dwarf, and the companion white dwarf survives the explosion, then it's moving very quickly at Roche lobe overflow, and it will zoom out of there at over 1,000 kilometers per second after the explosion. And so Ken used Gaia to search for these, and we found a few cases, 3 in particular, which have these high velocities. They are in this weird place in the HR diagram. They have very similar spectra to each other, and the interpretation there are these are the fastest unbound stars in the galaxy, and they are literally fugitive stars. They are fleeing the scene of their prime, which was to dump a bunch of material onto a white dwarf and make it explode, and now they are rushing out of it. So that's really exciting because that really points to the idea that at least some type 1a supernovae could be from double degenerate scenarios where the companion is not completely destroyed in the explosion. Similarly, speaking of not completely destroyed, there's the possibility that the white dwarf itself that explodes is not completely destroyed. So I alluded to this in the 1ax case, where the white dwarf might not be totally unbound, but there are these great observations of these very bizarre white dwarfs, and you all would know better than me how bizarre they are, studying white dwarfs. But anyway, these white dwarfs with enhanced abundances right in the intermediate mass elements and the iron peak elements that you would expect for nucleosynthesis from a white dwarf supernova. Okay? And how are these white dwarfs polluted with so much of this stuff? You can see like 2 orders of magnitude increase in abundance here. So the one idea that's really out there is that they are in fact the star that exploded, but it didn't completely destroy the star. Some fraction of it is being kicked out at relatively high speeds. So you can see this for this object here. And that material, that synthesized material, is still on the white dwarf. Okay, so these could be these 1ax explosions, these weaker explosions that don't unbind the star and run away partially burnt remnants of these. It's not completely.
Saurabh, sorry, can you please wrap it up?
Yep, I have. I think one more slide left.
Okay.
It's not completely sure because those models would predict a lot of unburned carbon, and that's not exactly seen in these spectra. So it's not. It's not a smoking gun, but it's certainly, whatever these are quite interesting and are likely related somehow to some kind of white dwarf supernova explosion. Okay, and as I said, yeah, so this is my last slide. There's so much I did not talk about. I see people in the audience who work on supernova rates and delay time distributions and supernova remnants, light echoes, there's all this other observational stuff that I did not get to, but all of this bears directly on the idea of progenitors and explosions. And it's really a rich field, and trying to bring everything together is the challenge. One thing I'll mention, which I just have to because what happened this morning, but soon there will be JWST observations in the mid-infrared, where we'll get access to, and there's a couple of approved proposals this morning that where we'll get access to these a new diagnostics of abundances and progenitors and explosion with JWST. So I just wanted to end with just emphasizing that there's this deep, rich connection between the white dwarf astrophysics, the supernova astrophysics, and then also the, oh, by the way, supernova distances and cosmology. And it would be great to strengthen the bridges between these different fields because the connections are so deep and so important. And with that, I'll end. Thank you very much.
Thank you, Saurabh. I think the statement that you're making fits exactly with why we, organized this meeting in the first place. So, well, thank you for, reinforcing the need for this even more. So if you have any questions for Saurabh, please push that button, raise your hands up. And I see already one question from Andrew Fullard. Do you want to?
Yes, thank you for the talk, Sarah. Very, very interesting stuff. Can you talk a little more about the mid-infrared observations? I saw that you got the JWST time. Congratulations.
Yeah, so our proposal was successful. Also another one by Chris Ashall. Our plan is to, now we're very excited about it launching. So our plan is to observe in the nebular phase, so about 150 or 250 days after maximum, where in the mid-infrared, what you get is these forbidden lines, not just of iron group elements, but also the intermediate mass elements. And so we'll get both near-infrared and mid-infrared spectra. We'll have 2 epochs, so we can watch the radioactive decay, for instance, the cobalt lines. And then we'll get diagnostics on like argon and some other lines, which are cleaner tracers of the intermediate mass elements than what you can see in the optical. And what's really exciting is the idea of looking for instance, stable elements at late times. So the predictions of the models, the Chandrasekhar mass models, predict explosions at relatively high density, where you get enough electron capture, so you get neutron-rich isotopes. So you make stable iron, stable cobalt, and stable nickel. And those then are not radioactive, of course, so they don't power, they don't power the light curve or anything like that. So what you would expect is this, stable nickel that stays, almost all the radioactive nickel will have decayed by that time. So you'll see stable nickel, and it's supposed to be near the center of the explosion as well. So you might see that in the line profiles, that the distribution of the stable nickel is different than the distribution of the iron 56, for example. Yeah, all of those diagnostics could lead to these questions.
Thank you very much. That sounds really exciting.
Wolfgang?
Hey, thank you so much for a really fun overview. So one of the things is obviously in proposals, we always churn this thing where we say like, there's this drama, we don't know the progenitors and like all of cosmology will fall apart. Obviously we want our colleagues to believe this, but I mean, to actually like, lean into our fear, like how much would we have to be off by to actually have a noticeable effect? How much would we have to have screwed up the understanding of how much nickel 56 or how much brightness is produced?
Yeah. So and that's a great question, Wolfgang. Adam Rees always asks me this question. Like, okay, say if you knew that the 1As were double degenerate, how would you change your cosmological analysis? And his argument is actually we try and design it so that it's insensitive to that, right? We try and make differential measurements so that things don't change. And I would say actually, for the Hubble constant measurement, things would not necessarily change that much. And so that's why when I try and write proposals, I say that the supernovae are important for cosmology, but I don't always, sometimes the reviewers make their own inference that, understanding the astrophysics will definitely improve the cosmology. But I don't try and say that explicitly necessarily. For H0, I think it would be hard because we do try and make those samples as similar as possible, but what the underlying progenitor is, it's very hard for it to change very much nearby and in the Hubble flow. So as I said, between 20 and 200 megaparsecs. But there are some things. There's still some, this local environmental effect. There are still some papers that argue that could be a few percent at least in H0, and so may go some of the way to resolving the tension. So for example, if you took a few percent from the supernovae and then a few percent from switching from Cepheids to TRGB, maybe you'd get all the way that you need to get to with one. I think it's a bigger uncertainty in the high redshift, in the dark energy, where people are trying to measure W to 1%, and the supernovae really provide a very orthogonal constraint compared to large-scale structure and other things. And so if we get that wrong by a few percent because the populations are drifting, and we don't really have a way of teasing that out, I think you could make a difference where someone says, aha, dark energy cannot be the cosmological constant, where it's actually supernova astrophysics that's causing it.
Thank you very much, and congratulations on the JWST time. Well done.
Ayandra, would you like to ask your question?
Yes, sorry, I couldn't unmute. Well, in the let's say to connect supernova with white dwarfs, one open problem in white dwarf modeling is what is the mass, like the limiting mass for a carbon-oxygen core and an oxygen magnesium core produced by a carbon plane. So you mentioned that the white dwarfs in these systems are most likely carbon-oxygen. I believe that you need that in order to explode because carbon is explosive and the others are not. So how can we help each other? Because, for instance, I would like to know that limit is between 1.05 and 1.1, but that depends a lot on the physics and the codes and the person you're asking. And I was wondering if we could actually use supernovae to have a limit.
Yeah, that's a great question, and I'm not the expert. I think there are more experts here. I would say one thing is that may be some motivation for these detonation models where the supernova is not Chandrasekhar mass, they're subchandra. And so there's sort of like one solar mass white dwarfs that detonate. And that also gives you a very nice type 1A, and it has, that's where you would expect carbon oxygen. For the higher mass, I don't know if it makes a difference whether that higher mass is achieved by accretion or if the white dwarf has time to, resort itself. And then also there's this idea not just of the oxygen, neon, magnesium, but these hybrid white dwarfs where there's some process, which again, I don't know the full details, where you have oxygen, neon, magnesium, but there is carbon that's still in the core and it sinks or it flips, or I don't know the full details. I saw Josiah is here.
Yes, I can answer, but Josiah is the expert. I actually asked this question to Josiah a few weeks ago. It's because carbon is ignited off center. So sometimes the carbon flame does not reach the center of the core. So if it gets just, I don't know, halfway from the surface of the core towards the center, then you will have these hybrid configurations.
Yeah, and by the way, you know, if that happens some fraction of the time, there's this whole range, this whole zoo of objects you need to explain. And I see a guy with his hand up too. And so, you know, it could be that situation does not necessarily lead to a normal 1A, but it could lead to something else.
Okay, I will.
Thank you.
I will ask Dean to start setting up his slides, and if a guy has a quick question, he can fire it.
Briefly
very hard to hear you, Hagai.
Oh, sorry. Can you hear me now?
Yes.
So just a brief, so I'll try to show just a brief comment. So in the double degenerate model, you could have mass transfer before the supernova, something we just briefly suggested for 19 EHK, but we're actually writing a paper which is much more general. The interesting thing about that, it connects to the white dwarfs because this mass which is transferred, or some of it is ejected before the supernova, when the supernova explodes, you could go through this material and you can actually probe the outer parts of the donor white dwarf. In 19 EHK, for example, you could see the hydrogen and helium layers and even actually identify how much mass was there. So in principle, this is kind of very early observation. You mentioned these bumps. If you actually had flash spectroscopy for those, like we had for 19 EHK, you could even really kind of do a tomography of the outer part of white dwarf. That would directly connect the white dwarf understanding, at least the outer parts, with supernova in that sense.
Yeah.
I have other comments.
And we tried to get on as soon as possible. I want to say one great shout out and thank you to all the people who are running surveys to find these supernovae young and early. That's been a huge shift that I didn't highlight, since 10 years ago. And so there is the possibility of doing exactly what you said, is get onto these very early and get spectra and whatever else observations you want.
Okay. I think Saurabh probably has to stop sharing his slides before Dean can put his up.